Thank you very much. Thank you very much, Raoul, and welcome everyone. Thank you for inviting me to talk to you this morning. So this is joint work with a colleague, Christoph Reisinger, and our PhD student, Filippo. So, okay, so this is the outline. This work is very much building on Stefan Heinrich's original multi-level Monte Carlo work on parametric integration. I'll explain that background, and then extending this in today's talk, talking about the extension to SDEs, but also Filippo has looked at extensions to PDE applications. So today's talk will really focus much more on the numerical analysis of this approach. Filippo is still working on lots of numerical examples, and future talks will emphasize that much more. And one bit I want to also talk about today is the issue of strong convergence analysis for pathwise sensitivities. This is something where I think possibly there's a gap in the numerical analysis literature. Either that or I failed to find the relevant bit of literature. So I'm hoping that if there's anybody there in the audience who knows about literature that I'm unaware of, that you will then tell me about it. Okay, so let's look at what we're after. So in Stefan's original work back in 2001, what he was interested in was the problem of parametric integration. He was trying to approximate a function, f of theta, where f of theta is defined as the expected value of some other function p, which is a function of a random variable omega and the parameter theta. Okay, and in his work, he assumed the ability to exactly sample omega and therefore p of theta and omega, and to do so at unit cost. So he was essentially looking at the finite dimensional omega problem. He was also assuming that f and p were both relatively smooth, which is an issue for us in the context of mathematical finance, where p is typically not smooth. So, in general, theta could be coming out of some domain, but let's just keep it nice and simple, and we'll shift and scale it so that we're taking theta out of a unit hypercube of dimension d. Okay, so d here represents the parameter dimension, nothing to do with any dimensions of the SDE or anything like that. So then in his multi-level setup, this is his telescoping sum, where he wants to approximate f by an interpolant of f on some fine grid in the parameter space for theta. And that can be decomposed into an interpolation I0, which is going to be a very coarse interpolant, plus a sequence of differences between improved interpolants. Okay, so in 1D, if we're operating on the unit interval from 0 to 1, then in 1D, the interpolant might be just simple piecewise linear interpolation. Okay, and on level L, the spacing would be 2 to the minus L. So as you go to higher levels, you have a refined interpolation. Okay, and then the natural extension of that into multiple dimensions would be to use a tensor product multilinear interpolation. Okay. So here's a simple example where the blue curve is the function f that we're trying to approximate. On level 0, we have the orange straight line approximation. And then we go to level 1 with the yellow approximation with 2 segments. And then level 2, we've got the purple approximation with 4 segments. The 2 main things to notice from this is as we go to higher and higher levels of approximation in the interpolation, then the difference between successive levels is getting smaller. And that's the key multi-level observation. And then the other key observation for later on in the analysis is that in comparing one level with the next level, the biggest difference is at the midpoint of the coarser interpolant. So in the yellow case, it's the difference between the yellow value at 0.5 compared to the orange value at 0.5, which is an average of its 2 endpoints. Okay, and that's going to come out in the analysis. Okay, so Stefan Heinrich then starts with his multi-level expansion, and then at each level of correction, he estimates the correction by doing Monte Carlo sampling in the omega space using some number of samples ml. And for each of those omega samples, it's evaluating it at all of the theta points necessary to construct the piecewise linear approximation. Okay, so as you're going to finer levels, the computational cost is going up because you're having to evaluate this at more theta points. However, because the difference in approximation is getting smaller as you go to finer levels, the variance is also going to 0, and so you don't need as many Monte Carlo samples in order to accurately estimate that quantity. Okay. So his analysis assumes that the number of theta points increases exponentially with the dimension d. And so the complexity that you end up with, this is the complexity to achieve a root mean square accuracy of epsilon, has the following order. Depending whether or not the dimension d for the theta parameter space is less than, greater than, or equal to 2 times r, where r is the degree of smoothness of f and p with respect to theta. Okay, so in the smooth case where it's twice differentiable, so r is equal to 2, then we're getting the sort of optimal complexity if the dimension is less than 4. If it's equal to 4, then we get the extra log epsilon squared term. If it's greater than 4, this is where we're starting to be hurt by the curse of dimensionality as we go into higher dimensions. Okay. Please, by the way, ask questions if you like as we're going. I've got the chat window in front of me, so hopefully I can see you if anybody does raise a question. Okay, so that work of Stefan's is very much the starting point for our current research. And so we've taken this and extended it in a number of directions. So one aspect is using it also in cases where f of theta corresponds to a functional arising from a PDE solution. So then there's nothing stochastic about this, but we still have the multi-level expansion where we're looking at the fineness of the grid being used in the PDE approximation. Okay, but we aren't going to talk about that today. There's also the issue of going from the tensor product multilinear interpolation to using sparse grid interpolation. So this is really addressing the curse of dimensionality, and that has worked particularly well for the PDE applications. Relevant to today's talk is weakening the assumptions on the smoothness of the random quantity P. That in computational finance applications, that rarely is twice differentiable. Also, thinking of computational finance, often we have to approximate stochastic differential equations, and so we're interested in the issues that raises and how that gets integrated into the whole algorithm construction and then the analysis. And then we'll be talking about the numerical analysis on the SDE side. Filippo has also looked at the numerical analysis on the PDE side, which is particularly concerned with sparse grid interpolation and proving the necessary degree of mixed derivative smoothness. Okay, so for the parametric integration, this is a slight generalization of the sort of meta theorem, multi-level analysis that Stefan Heinrich did, that you assume that you have some known order of convergence of the interpolation of f, the expected value function, so that as you go to finer and finer levels, that interpolation error decays proportional to 2 to the minus RL. So that's the same R that Stefan had. But then with the variance, we're allowing that to have a different order of convergence. So 2 to the minus SL. In Stefan Heinrich's work, he was assuming that S was equal to 2R. We're extending that because we may not have the necessary degree of smoothness for Y. So Y here is any unbiased estimator for f of theta. Okay, and then this is the corresponding sort of generalized result on the complexity to get the epsilon root mean square accuracy. Now, in 1D, using the linear interpolation, the thing I pointed out previously when we were looking at the figure is that the biggest difference between a coarse and fine interpolant is at the midpoint of one of the coarse theta intervals. So in the numerical analysis, what we're interested in bounding is this second difference of Y with respect to changes in theta, the parameter. So for the same omega, we're evaluating Y at the midpoint, which is theta 0, and at the two endpoints, theta 0 plus delta theta, theta 0 minus delta theta. Maybe I'll just quickly go back to that plot there. Okay, so we're looking in terms of the difference between the yellow and the orange lines. We're looking at the difference between the yellow line at 0.5 and the orange line at 0.5, which is the average of the two endpoints, 0 and 1. Okay, so that difference is actually, well, it's 1/2 of this delta squared Y quantity. Okay. And we're motivated by applications in mathematical finance for which our capital P, so payoff value, is some function little g of the terminal value of an SDE. So an SDE solution at the terminal time capital T. Now, there may be other financial functions that we're interested in the future, but currently we're just looking at this simple European option case. Okay, and omega here represents the driving Brownian motion that's being fed into the SDE simulation. Okay. So first of all, we can consider the case where we have an integrable SDE, which is, there are very few of these, but things like geometric Brownian motion, an Ornstein-Uhlenbeck process, where you can directly and exactly simulate ST at that terminal time. Okay. Now, in the case of the integrable SDE, then, we assume that the SDE we have is such that moments of the ST are all finite, and also that the drift and diffusion coefficients are smooth with respect to theta, so infinitely differentiable, such that we also have bounded moments for all derivatives of ST with respect to theta. This can be proved under sort of standard conditions, though I haven't yet found a reference for that. And I'll come back to this issue of the analysis of derivative quantities later. Okay. So if the payoff function were to be twice differentiable, then y dot, so I'm using dots here to signify a derivative with respect to theta. So y dot is g prime s dot. So g prime is the derivative of g with respect to s. And then y double dot, the second derivative with respect to theta, is g double prime s dot squared plus g prime s double dot. Okay. So, if we have sufficient smoothness for g, then y dot, y double dot are both well defined, have bounded moments, and then we can express delta squared y, the second difference operator. We can express that as an integral over the interval from theta naught minus delta theta up to theta naught plus delta theta of that weighting term multiplying the y double dot. And so on the basis of this, you get the fact that delta squared y is of order delta theta squared, that the expected square of delta squared y is of order delta theta to the fourth. And so this gives us back the nice smooth case analysis of Stefan Heinrich with s equals 4 and r equals 2 in the meta theorem. But in mathematical finance, having twice differentiability is, I'm not sure it ever happens. Okay. So let's then go to the opposite extreme. Let's suppose that we're looking in finance terms at a digital option. So a digital option is something that pays out either 0 or 1. So it pays out 1 if ST belongs to some set K. Okay. Now, in analyzing this, we follow a sort of line of research from previous work, where we assume that there's this constant C such that for all theta and for all small distances delta, the probability that ST lies within a delta neighborhood of the boundary of K is less than this constant C times delta. Okay, so heuristically, you can think of this as essentially saying that we have a bounded density on S of t, but it also actually requires the set K to not be really weird. You know, even if your ST had a nice bounded density, it is possible to construct really bizarre domains K such that this condition would not be satisfied. And so, you know, Haji Ali and I have done some analysis of this in a different paper where we give conditions under which this assumption is satisfied, and also illustrate, you know, problems in which, because of K being weird, this condition is not satisfied. Okay. So then, given that assumption, the heuristic analysis is that, you know, for a given theta naught, there's an order delta theta probability that your ST ends up being within order delta theta of the boundary. Okay. And I'm interested in that delta theta sort of region, because what I want to look at is ST of theta over the range from theta naught minus delta theta up to theta naught plus delta theta. So that whole sort of curve. Because what this gives then is an order delta theta probability that that little segment of ST as a function of theta, that crosses the boundary delta K. Because in that case, this second difference, delta squared y, will be of order 1. On the other hand, if it doesn't cross the boundary, then all 3 points are on the same side of the boundary, and in that case, delta squared y is equal to 0, because either they're all equal to 1 or they're all equal to 0. And so therefore, we get the fact that the expected square of delta squared y is of order delta theta. Okay, so that's a heuristic analysis. The rigorous version of that analysis, you can't quite get the delta theta to the 1 power, but you get it as being little o of delta theta to the 1 minus a little bit. You know, this is a slightly different delta now that I've got in that exponent, but it's any little delta greater than 0. So roughly speaking, we have S of approximately 1, and R is still equal to 2. In the Lipschitz case, where we have a bounded second derivative everywhere except on this boundary delta K. So I'm thinking of things like European put-call functions for those who are familiar with, you know, the mathematical finance context. So it's piecewise smooth, it's continuous. Then the heuristic analysis is, again, there's an order delta theta probability that we cross the boundary. But now, because it's Lipschitz, if we do cross the boundary, that delta squared y is now of order delta theta rather than being of order 1. And if we don't cross the boundary, then because we're assuming there's a bounded second derivative everywhere else, the delta squared y will be of order delta theta squared. But then putting those two pieces together, the dominant contribution comes from the ones that cross the boundary, and so the expected square is of order delta theta cubed. And so we end up with S being approximately equal to 3, R being equal to 2. So it's a little bit worse than the S equals 4 case when it's a completely smooth function, but it's still pretty good. Okay, so that's for integrable SDEs, but most SDEs in mathematical finance are not integrable. So instead, we need to approximate them using something like a simple Euler-Maruyama discretization. Okay, so here I'm assuming you're familiar with, you know, standard multi-level for doing path approximation, where we have the telescoping sum with respect to the time step, that as we go to finer levels, we're using smaller and smaller time steps. Okay, and standard multi-level analysis for these path problems is that if the time step decays like 2 to the minus gamma L, so that means that the cost is going up like 2 to the gamma L. If the variance behaves like 2 to the minus beta L, the weak error behaves like 2 to the minus alpha L, then we get the optimal complexity in the case where beta is greater than gamma. Okay. Now, in that case where beta is greater than gamma, one option is we can use the randomized multi-level of Rhee and Glynn. And so there, this Y, I said that Y just needs to be an unbiased estimator for the expected value of P. In the randomized multi-level, this unbiased estimator Y is defined this way. So we have little p L prime inverse times delta capital P L prime. So L prime is a random index. And it's a random index chosen with a probability as defined there, proportional to 2 to the minus beta plus gamma L over 2. So you choose this random level, and then for that random level, you evaluate delta P, the difference in the payoff value between the fine and the coarse approximation. And this works as an unbiased estimator because the expected value of Y is a sum over all of the levels that exist of the probability that the random variable L prime corresponds to that particular level times this quantity Y. But then the probability that L prime is equal to L is that little PL, and so they cancel out, and so you just get the sum over levels of delta capital PL, and that is the payoff value. And actually, I realized that I should have expectations around all of this. So I should be getting, yes, I should have expectation of delta PL and expectation of P there. So I need to correct that slide. Okay. Okay. Alternatively, if we don't want to do the randomized multi-level, the alternative is to use a multi-index approach, as done by Raul and Fabio and Al in 2016. And so here we start with the multi-level interpolation decomposition that we had before. And then each of the Fs we can replace by a time step approximation expansion. Okay, so we have sort of two indices in our multi-index, where one index corresponds to interpolation and the other index, L prime, corresponds to the time stepping approximation of the SDE. Okay. And yeah, we end up with this double summation in L prime space. And then each of these quantities we then have to estimate by a Monte Carlo estimate. Okay, so we end up with our approximation F tilde being this double indexed sum of Monte Carlo estimates, on each of the elements in the multi-index expansion. Okay, and so the number of samples we choose is going to be varying for each one of these terms. Okay. And then what we want to do is to optimize what are the terms that we include in the multi-index expansion, and then for each of those terms, how many samples do we want for the Monte Carlo estimator? Okay, and so we have an expression for the error in the final approximation. We can bound that so we can control the some weak error in the approximation, and then we have an expression for the variance of the estimator, and we try to optimize the variance for a given computational cost. Okay, and then following the multi-index analysis from that paper by Al and Fabio and Raul, if you make assumptions about the nature of the convergence of the weak error and the variances, you have a total computational cost. Then you can, there's a meta theorem to give you what is the complexity to achieve a particular root mean square accuracy of epsilon. Okay, and in the best case, you get a cost of order epsilon to the -2, and it depends on this quantity eta. And so in some cases, you're limited by what's happening with the interpolation accuracy and cost. In other cases, you're limited by what's happening with the approximation of the SDE and the corresponding cost of that. Okay. But the key thing from a numerical analysis point of view now is that we need to look at that assumption for the variance and see if that is indeed what we get in our analysis. Can we bound that? Okay. And so the challenge is to bound this quantity, the variance of difference in interpolation levels applied to a difference in the time stepping approximations. Okay. So if we're on a level that has a spacing of delta theta and on a time step level L prime that has a time step of h, then this is what we're trying to bound. It's the variance of this sort of 6-term sort of difference where we have a second difference in the theta direction. That's what comes from the interpolation error. But we also have a difference in the time step, with the top line there being the fine time step of h, and the bottom line being the coarse time step of 2h. Okay. Now, in the smooth case, you can show that the variance you get is of order delta theta to the 4 times the time step h. That's for the Euler-Maruyama case. For the Milstein, it'll be delta theta to the 4 times h squared. And so that's that nice product form that you sort of want for the multi-index meta theorem. So that works out nicely in the smooth case. The challenge then is what happens in the non-smooth case. And so in the non-smooth case, we end up with a whole bunch of different possible scenarios to consider. That in these plots, the lines labeled A, B, C, D, this is this boundary delta K, where it's in the digital case, it's separating payoffs of 0 and 1. In the case of the Lipschitz function, this is the point at which things are not differentiable. Okay. So I said we were looking at this difference of 6 points, And so in these two figures, those 6 circles correspond to the ST values. So this is a two-dimensional SDE being illustrated here. And those 6 circles correspond to the 6 values at which the function g is being evaluated. In scenario 1 on the left, we've got the case where the square root of h is smaller than delta h. And so what you see are those 6 points grouped as sort of 3 pairs of points. Each of those pairs of points being close together because the time step is very small. In the right-hand scenario, that's the case where the time step is much greater than delta theta. And so you have 2 groups of 3, and those groups of 3 correspond to the same time step, but different theta values. So then you look at the different possibilities of how the boundary delta k sort of interacts with these 6 points. And for each of these different scenarios, there are different probabilities, and you just work your way through all of those possibilities. And eventually, this is what you end up concluding. That for the Euler-Maruyama discretization, in the digital case, we don't get the nice sort of product form between delta theta and h. Instead, we get something where it's the minimum of either h to the half or delta theta. And then in the Lipschitz case, it's the minimum of either delta theta h or delta theta cubed. So it's not of the form that is assumed in the meta theorem. The analysis then has to be extended to the meta theorem. And I haven't actually done that yet. That's on my to-do list. Okay. How am I doing for time? Not too badly. Okay. Okay, so I want to say a bit about this issue of strong convergence for pathwise sensitivities. In doing the numerical analysis, what we need are some strong convergence results. So S dot I've already described as being the derivative of S with respect to theta. So that's the pathwise sensitivity. S dot hat is the Euler-Maruyama approximation of that. And you can think of that either as the Euler-Maruyama discretization of the equation for S dot, or you can think of it as the theta derivative of the Euler-Maruyama discretization for S. You get the same thing either way around. And what we need is for that to have the same half order of convergence that we have for the regular S hat, Euler-Maruyama discretization of the SDE. And we also need it for S double dot, the second derivative. So this can be proved. I've proved it. I kind of feel like this ought to exist somewhere in the literature already, but I have failed to find it in the literature. So if anybody there has seen this result previously, I would be very pleased if you would tell me about it. Okay. So to keep things simple, let's just stick with the autonomous SDE. So we'll drop out the time dependence from the drift and the diffusion coefficients. What are referred to as being the usual conditions for analysis are that A and B are globally Lipschitz. Okay. And if they are globally Lipschitz, then the SDE has a unique solution, and we have these standard results that all moments of S are bounded, and the difference between st and st naught, over a small time interval, that grows like t minus t naught to the half power. Okay, so those are standard results for the usual conditions. And for Euler-Maruyama approximation, we then get half-order strong convergence for the approximation. And this is a key aspect of analyzing multi-level path-based algorithms. But if we now look at what's happening in sensitivity analysis, well, let's keep things simple. Let's do a case where f is scalar. A and b depend smoothly on scalar parameter theta. We're interested in the value of this expected payoff function. We want to compute its derivative. So if P is globally Lipschitz, piecewise smooth, then f dot, the theta derivative, is the expected value of P dot, where P dot is dp ds times S dot. And S dot satisfies the pathwise sensitivity equation that comes from differentiating the original S equation with respect to theta. Okay, so we get an A dot plus A prime S dot, B dot plus B prime S dot, the W. Okay, I'm avoiding having explicit dependence of the initial condition and the payoff on theta, but it's easily extended to include that. Okay. Then we have the natural Euler-Maruyama discretization of that, and it's the same equation that one would get if you started with the original Euler-Maruyama discretization and then just differentiated with respect to theta. Question then is, what is the strong convergence of S dot hat to S dot? I feel somewhat embarrassed about this. I supervised a PhD project 10 years ago in which the student and I assumed that this was true, and we thought at the time that it was obvious that it was true. However, in retrospect, it's not obvious that it's true, that we have half-order strong convergence. And I have failed to find a reference for this in the literature. Okay, so let me explain this. So what we said in that original work was that you could take the S dot equation and sort of append it to the regular S equation and think of this as a vector SDE. And then we said, oh, well, let's say this vector SDE satisfies the usual conditions, hence we get half-order strong convergence. However, in general, that is not true, that the vector SDE satisfies the usual conditions. Because when you look at the pathwise sensitivity equation, the problem here is the A prime S dot term and the B prime S dot term. That if you look at those terms and you apply the test to see whether you have global Lipschitz condition, what you find is you get this piece A double prime times V2 times V1 minus U1. That's the nasty term, that unless A double prime is 0, and in all cases, you have that A double prime V2 tends to infinity as V2 tends to infinity, and therefore you do not have the global Lipschitz condition. Okay, because we have that A double prime V2 bit multiplying the V1 minus U1. So it's got the right form for the sort of Lipschitz test, but the A double prime V2 is not bounded. Okay. And in fact, it becomes even more obvious when you look at the second order pathwise sensitivity equation, that I've got the first order one there, and then you just differentiate a second time. And when you look at the S double dot equation, you're now seeing things like A double prime S dot squared. And as soon as you see that S dot squared term, that's not globally Lipschitz. So the usual conditions are not satisfied, except in the case of geometric Brownian motion, basically, when the A double prime and the B double prime are 0. However, and this is the key point, if you look at the S dot equation, then on the right-hand side, S dot is multiplied by A prime and by B prime, and they're both bounded. And in the second equation, the S double dot equation, on the right-hand side, S double dot is again multiplied by A prime and by B prime, and they're both bounded. And it's the fact that they're bounded that ultimately means there isn't a problem here, that everything works out nicely. Okay. There is a lot of literature on dealing with problems which are not globally Lipschitz, using all kinds of modified numerical approximations. But the point is, we don't need any of that here, that there isn't a problem with the pathwise equations. Really, it's only a problem with the numerical analysis that, as far as I can see, this hasn't been considered in the literature. And so all we need is new numerical analysis to prove that everything is well behaved. And it really isn't difficult. You just have to go back to the standard analysis, including the Platen, and essentially follow the same path that's used there, and just modify the analysis to account for things. So again, as it says here, the key point is that in the drift and diffusion terms, the S dot is multiplied by something that's bounded. And for the other terms, we've got arbitrary moments. All of the moments are bounded for S and S hat from the usual analysis. And so, the fact that those bits don't have that sort of Lipschitz behavior doesn't matter. And beyond that, basically, it is just the standard methodology. I'm going to give the lemmas, but the methodology to prove these is pretty standard. So you first prove that for the SDE, S dot has all bounded moments. You also have to do the short time analysis to show that growth behaves like t minus t naught to the half power. You then have to prove that the Euler-Maruyama approximation, all of its moments are bounded. And then finally, you prove the strong convergence result. So essentially, it's just retracing the steps of the standard analysis, doing the extra pieces that are necessary. Okay. So that's done for this simple scalar case, done for the first order. Higher derivatives follow naturally. Basically, it's a bootstrapping process. You start with S, then that gives you what you need to prove the result for S dot, and then that gives you what you need to prove the result for S double dot, and then by induction you get all the higher derivatives. I've only written things out for the scalar case, but vector SDEs are not a problem. If we have time dependence in the drift and volatility, I don't see that as being a problem, particularly if we just say that they have bounded derivatives in time. I suspect it is sufficient for the theta and S derivatives to be half Holder in time. Other discretizations, my guess is it's probably fine for the Milstein discretization as well. I mean, certainly computationally, we've never had any problems with doing these pathwise sensitivity calculations. So I think it is just a lack of numerical analysis in the literature, unless and any of you are aware of literature covering this. Okay, let's wrap things up, and that'll leave some time for questions. So I think we've sort of extended what's there in terms of approximating parametric functions arising from SDE calculations, and nearly optimal in terms of having usual epsilon to the -2 complexity in a number of cases, or optimal in the sense that you can't do any better given the limits of approximating the SDE or approximating the interpolation. So we have a good amount of numerical analysis now. We have very limited numerical results, but the ones that we have so far do support the analysis. So Filippo, our students working on a lot more numerical computations now. Extending the analysis to sparse interpolation, that's something that he's been able to do in the PDE case, where it's possible to do the analysis for the mixed derivatives. However, you need very high order mixed derivatives in the sparse analysis. I think for the SDE case, that looks incredibly challenging. So I don't hold out a lot of hope for doing that. Also, for these non-smooth cases, I think that the path branching work that Al and I have done previously could significantly improve the variance. I think the use of conditional expectations can also improve the variance for non-smooth cases. And so these may be things that we investigate in the future. And then, references. So these are some of the things I've talked about. Okay, so thank you very much, and I'll be happy to try and answer your questions now.